Today we are diving headfirst into one of the most violent, literally, high-energy phenomena in the entire universe. We're talking extreme plasma physics. Specifically, we're looking at atmospheric electrical discharges. Yeah, lightning. But we're going to strip away the meteorology and look at it purely through the lens of extreme thermodynamics. So let's get right into it. 30,000. Just let that number sink in for a second. 30,000 is the peak temperature in Kelvin of the plasma inside a standard lightning return stroke right here on Earth. In literally a fraction of a millisecond, a narrow column of just everyday air gets violently superheated to this totally incomprehensible extreme. And that immediately brings us to this massive, kind of myth-busting question. We hear it all the time, right? Is a lightning bolt actually hotter than the sun? It sounds like a total exaggeration. How on earth could a localized storm cloud on our little blue planet whip up something hotter than a thermonuclear star?
So, looking at the numbers, the answer is a definitive yes. The core of a terrestrial lightning bolt, sitting right at that 30,000 Kelvin mark, is roughly 5 times hotter than the solar photosphere. That's the visible surface of the sun, which hums along at a relatively cool 5,772 Kelvin.
Now, you might be wondering, how do we actually know the sun's temperature without, sending a thermometer 93 million miles away just to watch it melt? Well, astrophysicists use this really elegant piece of math called Wien's displacement law. It basically says that the peak wavelength of light emitted by a black body, like our sun, is inversely proportional to its temperature. Since the sun's spectrum peaks around 500 nanometers, scientists can perfectly calculate that 5,772 Kelvin baseline without ever having to touch the thing. But okay, to be completely fair to our star, we really need to look at its extended atmosphere. This data perfectly illustrates what astrophysicists call the coronal heating paradox. Check out that bottom row. As you move further away from the sun's nuclear core, past its surface, the temperature absolutely skyrockets to an insane 1 to 5 million Kelvin in the corona. So yeah, while lightning easily beats the sun's surface, the sun's outer atmosphere definitely reclaims the extreme heat crown.
So how does it get so incredibly hot that far from the core?
NASA's Parker Solar Probe actually flew straight into this 1,700 degree Fahrenheit atmospheric layer to find out. And it detected magnetic field lines twisting, stressing, and then explosively snapping back together. This magnetic reconnection releases catastrophic amounts of energy into the plasma. And honestly, here's the most mind-blowing part of all of this. That magnetic snapping, it is essentially just a vastly scaled-up version of the exact same dielectric breakdown that causes lightning right here on Earth.
Which brings us back down to Earth. We know how to measure the sun from afar, sure. But how do you measure a 30,000 Kelvin plasma bolt that only lasts for a few microseconds? And how do you do it without instantly vaporizing your thermometer? Because obviously sticking a physical probe in there is just not going to happen.
Enter this absolutely incredibly named piece of tech, SOPAPILA. That stands for the Spectrally Resolved Optical Automated Photometric Instrument at Langmuir Lab. Try saying that 3 times fast. Instead of a physical probe, this thing is a high-speed photodiode array. It captures near-infrared light at a staggering 800,000 times per second. By meticulously filtering out all the background continuum radiation, it perfectly isolates the light emitted purely by excited atomic oxygen. And that is what allows scientists to calculate the exact kinetic temperature of the plasma. And here is what that data actually shows us. SOPAPILA cuts right through the blinding white flash to reveal the exact thermal decay of the bolt. Just look at these distinct phases. The initial return stroke surges to nearly 35,000 Kelvin. But even the precursor dart leaders, the ones just kind of prepping the channel, they're hovering around 15,000 Kelvin. It is this highly dynamic, microscopic dance of raw energy. And when all that massive, fleeting energy slams into the ground, it physically scars the Earth. That 30,000 Kelvin thermal shock violently seeks the path of least resistance through the soil. In literal milliseconds, it pushes way past the 1,700 degrees Celsius melting point of silica. It instantly vaporizes moisture and melts ordinary dirt and sand into hollow tubes of pure glass. We call this fossilized lightning. These fossilized structures are officially known as fulgurites, and they come in a few different flavors depending on what the lightning actually hits. Type 1 hits sand, creating these massive, hollow, branching glass tubes. Types 2 and 3 hit organic soil, leaving behind dense clumps full of trapped, rapidly burned carbon. Type 4 strikes solid mountain peaks, leaving glassy crusts right on the rock face.
There's even an exogenic type, where the lightning instantly melts dust right out of the ambient air into these tiny little glass spheres.
Because these fulgurites are forged in such unimaginable extremes, lightning is literally creating brand new geology. In fact, recently, inside a fulgurite excavated in Florida, scientists discovered a highly unusual, colorful form of calcium phosphate. Before this, that exact molecular arrangement had literally only been seen in meteorites from deep space. The extreme plasma physics of a local lightning strike forged an alien-like crystal right here in Earth's dirt. Now, to put things into perspective, an average strike delivers about 1 gigajoule of energy. That is roughly equivalent to the explosive kinetic energy of a quarter ton of TNT. So here's a paradox that seems to totally break the laws of physics. If a strike is really that powerful, how on earth do 70 to 90% of human beings hit by lightning actually survive?
The answer to that wild statistic actually lies in trauma medicine and something called the surface flashover effect. When a bolt approaches, the victim is usually already wet, right? Either from rain or physiological sweat. Well, that moisture acts as a highly conductive surface layer. Because the human body is highly resistant internally, that massive electrical current takes the path of least resistance. It arcs right across the wet exterior skin, entirely shunting the deadly energy around the vital organs. The intense heat then instantly vaporizes that sweat, causing a miniature steam explosion that literally blows the victim's clothes and shoes right off. I know, it sounds absolutely brutal, but it's literally physics saving lives.
And the physical aftermath of surviving a flashover like this is visually stunning. The immense electromagnetic field flowing over the skin can actually rupture delicate surface capillaries. This leaves behind what are known as Lichtenberg figures. They are these branching, fern-like red patterns that perfectly trace the path of the electrical discharge. They look exactly like temporary lightning tattoos, and thankfully, they usually fade away in a few days without any permanent scarring. Okay, for our grand finale here, let's rocket out into the solar system. Because the laws of plasma physics certainly don't stop at Earth's atmosphere, and understanding them here helps us decode the entire universe. Just compare Earth's storm conditions to Jupiter's. Down here, light water vapor easily rises through our nitrogen and oxygen to create storms. But on Jupiter, that atmosphere is dense hydrogen and helium, which means water vapor is actually heavier than the surrounding air. So it takes brutal, massive thermal energy just to get a storm started. To even generate lightning on a gas giant, massive internal heat radiating from deep within Jupiter has to force that heavy, moisture-laden air to literally punch upward through the dense hydrogen. This creates colossal thunderheads, towering 100 kilometers high. That is 10 times taller than Earth's absolute worst storms. And because the storm is just so incredibly massive, the dielectric breakdown voltage required to finally spark a lightning bolt is exponentially higher. When it finally snaps, it sends intense radio wave pulses, called spherics, echoing all the way out into deep space. And when a Jovian lightning storm finally breaks, it doesn't just rival our storms, it completely obliterates them. Data from spacecraft like Juno have revealed that these deep atmosphere discharges, often referred to as superbolts, can be up to 1 million times stronger than the most extreme high-energy lightning flashes ever recorded on Earth. Which leaves us with this final thought. We know that the relatively tiny spark of Earth's lightning, just a single gigajoule at 30,000 Kelvin, is enough to instantly melt solid rock into glass and forge alien meteorite crystals in our soil. So, if Jovian superbolts are 1 million times more powerful, what exactly are they leaving behind in the dark, crushing depths of Jupiter?
What the fact? Follow for more.